At 24,000 feet over Hawaii, the ceiling above the first rows of Aloha Airlines Flight 243 disappeared. The failure ran through the upper fuselage behind the cockpit. About 18 feet of skin and supporting structure separated from the Boeing 737 while it was still moving at airline speed. Air, insulation panels, and loose objects were pulled toward the opening. 95 people were aboard. Flight attendant Clarabelle Lansing, standing in the cabin, was swept from the aircraft and is presumed to have died. Passengers and another flight attendant were seriously injured. The pilots could hear almost nothing over the airflow. The airplane did not break apart. Its floor, lower fuselage, wings, and enough of the cockpit connection remained intact. That surviving structure gave the crew one chance to descend and reach Maui. The opening looked sudden. The damage behind it had accumulated through years of pressurization cycles, failed bonding, corrosion, and cracks that inspection had not contained. Flight 243 left Hilo for Honolulu on April 28, 1988. The aircraft was N73,711, a Boeing 737-297 operated on short inter-island sectors. Captain Robert Schornsteimer and First Officer Madeline Tompkins were on the flight deck. 4 flight attendants worked the cabin, serving 89 passengers. Hawaii's route network made short flights routine. Every climb pressurized the fuselage. Every descent released that pressure. The airplane's calendar age did not describe the full structural history. The number of pressure cycles mattered because each cycle stretched the cabin skin outward and then allowed it to relax. The day's earlier flights had not produced an unmistakable warning of imminent separation. The final sector began as another brief trip between islands. The structural threat sat inside a longitudinal lap joint, beneath paint and sealant, where external visual inspection had to find damage before many small cracks became one continuous failure. An airliner fuselage is a thin pressurized shell reinforced by frames, stringers, and joined skin panels. Cabin pressure pushes outward across a huge area. The structure distributes that load through curved aluminum skin and the joints connecting one manufactured panel to the next. On early 737 construction, longitudinal skin panels overlapped at lap joints. Rivets carried mechanical load, while adhesive bonding was intended to improve load transfer and seal the joint. The overlap looked narrow, but it ran along a large portion of the fuselage and experienced stress during every pressurization cycle. A sound joint spreads load. A disbonded joint concentrates more load around rivet holes and sheet edges. That changes fatigue from a slow, distributed process into repeated local damage. The cabin does not need one spectacular overload. Normal pressure can grow cracks when the intended load path has already deteriorated. The joint at the center of Flight 243 was identified as S10L on the left side of the upper fuselage. The designation located a longitudinal seam. Investigators found significant disbonding and fatigue damage there. The failure then propagated through the upper lobe between fuselage stations 360 and 540. Adhesive disbonding meant the intended bond no longer shared load reliably. Moisture and corrosion reduced durability. Rivet holes became local stress raisers. Repeated cabin pressure cycles opened and extended cracks through the sheet beside those fasteners. The dangerous condition was not one isolated crack growing alone. Damage existed at multiple locations. When neighboring cracks linked, the remaining skin between them could no longer arrest the opening. A joint designed to tolerate local damage behaved like a perforated tear line. Fatigue is damage from repetition. Cabin pressure on one flight is well below the load intended to break a healthy fuselage. Applied thousands of times around a weakened joint, the same normal load can extend microscopic cracks a little farther on each cycle. Island service is especially demanding in cycle count because one flight may last less than an hour while still containing a complete pressurization and depressurization event. Long-haul aircraft may accumulate more hours, but a short-haul fuselage can accumulate cycles much faster. Hours measure how long an airplane has flown. Cycles measure how often certain loads have been applied. Maintenance planning needs both. Flight 243 made the distinction visible. The structure failed during a normal cruise pressure condition because its repeated load history had already changed the joint. The NTSB traced the condition beyond one airplane. Early production 737 cold bond lap joints had experienced durability problems. Manufacturing difficulties could leave bonds that did not retain their intended strength. Once disbonded, the joint became more vulnerable to moisture, corrosion, and premature fatigue cracking. Boeing had issued service information and inspection proposals. The FAA had issued an airworthiness directive, but the NTSB found that its required scope did not cover all lap joints proposed in the relevant Boeing Alert Service Bulletin. The defense existed, but it did not reach every location the manufacturer had identified. A service history becomes safety information only when it changes inspection, repair, or retirement action. Flight 243 exposed a gap between knowing that early joints had difficulties and requiring a complete terminating solution across the affected structure. Corrosion does more than remove metal. It can break adhesion, create pits where stress concentrates, and hide beneath overlapping surfaces. In a coastal operating environment, moisture and salt exposure make sealing and inspection discipline especially important. The lap joint's exterior could appear continuous while damage developed inside the overlap. Paint condition, sealant, rivet appearance, and subtle surface changes became clues. Finding the true condition could require close inspection and, in selected areas, non-destructive methods capable of revealing cracks not obvious to the eye. Inspection quality depends on access, lighting, surface preparation, instructions, training, and enough time to examine the full required length. A crack detection rule is only as strong as the maintenance system that turns it into a repeatable task. At 1:46 in the afternoon, the aircraft was level at 24,000 feet. Cabin pressure loaded the damaged joint outward. A local section failed, pressure forced the opening wider, and cracks raced through the already weakened upper skin. Decompression did not politely remove one panel. Air escaping through the breach loaded surrounding structure and pulled interior material toward the opening. The upper fuselage peeled away aft of the entrance door. The cockpit remained attached through the floor and lower structure, but the flight deck and cabin were now separated by noise, airflow, and severe damage. The speed of the event exceeded human reaction. The maintenance history determined what broke. The crew's work began only after the structure had already changed shape. The cabin environment changed instantly. Oxygen masks deployed, but the open structure exposed occupants to violent airflow and debris. Seatbelts became the primary restraint. People not secured tightly faced far greater movement than a normal decompression scenario assumes. Clarabelle Lansing was working in the aisle and was swept from the aircraft. The NTSB lists her as the fatality. 7 passengers and 1 flight attendant were seriously injured. Many others suffered minor injuries. The human cost belongs in the explanation because structural design and inspection protect occupied space, not an abstract pressure vessel. Survival inside the remaining cabin depended on seat attachment, belt use, floor integrity, and the aircraft staying controllable long enough to descend into denser air. Winds. In the cockpit, communication became extremely difficult. The pilots used oxygen masks and began an emergency descent. The damaged fuselage changed airflow around the aircraft and raised questions the checklists could not fully answer: how much structure remained, how controls would respond, and whether configuration changes would impose new loads. Kahului Airport on Maui offered the nearest suitable runway. Turning toward it reduced time at altitude and avoided extending the flight toward Honolulu. Controllers supported the diversion while the crew concentrated on descent, speed, and basic control. The correct response to decompression is to reach breathable altitude quickly. Here, descent also reduced pressure differential across the torn fuselage. Lower altitude could not repair the structure, but it reduced the force trying to push the cabin outward. The flight crew could not see the full extent of the missing upper cabin from their seats. Instrument indications described airplane systems, not the shape of the fuselage behind them. Reports from the cabin were constrained by noise and damage. The pilots had to fly conservatively with incomplete structural information. Speed mattered. Higher speed could increase aerodynamic loads on exposed edges. Lower speed reduced some loads but narrowed margin above stall, particularly as landing configuration changed. Turns, flap extension, and gear deployment each had to be considered against an unknown structure. The aircraft's survival did not prove that the remaining structure had comfortable margin. It proved only that enough capacity remained for the actual descent and landing path. Approach configuration imposed another set of choices. Landing gear and flaps add drag and change structural loads. A normal checklist assumes a normally shaped airplane. Flight 243 required the crew to obtain landing performance while avoiding abrupt changes that could worsen damage. Kahului's runway gave the crew a clear physical target. Airport rescue teams could prepare while the 737 descended over Maui. The pilots kept control through final approach and placed the damaged airplane on the runway. Photographs after landing show why the outcome remains difficult to process. The wings, engines, tail, cockpit, and lower cabin stand on their landing gear. Above the first rows is open sky. The airplane appears both intact and destroyed because different structural load paths had reached very different states. Once the airplane was on the ground, investigators could map the fracture. The missing upper skin extended from near the forward cabin entrance aft across approximately 18 feet. Fracture surfaces, remaining rivet rows, corrosion, and crack patterns identified where the failure began and how it spread. The S10L lap joint provided the starting line. Disbonding reduced the joint's intended behavior. Fatigue cracks existed at multiple rivet holes. When pressure opened the structure, those cracks linked across the weakened sheet. The visual drama of the missing roof was the final state. The evidentiary value lay at the edges, small regions where metal recorded thousands of prior loading cycles and the direction of the last rapid fracture. Investigators distinguished fatigue from the final overload. Fatigue surfaces record progressive crack growth under repeated loads. The last separation leaves a different fracture character where the remaining material fails rapidly. Reading both regions separates damage that existed before the flight from damage created during decompression. Corrosion deposits and disbonding added context. They showed that the joint had not been behaving as a fully bonded assembly. The problem was mature enough to demand detection before the accident flight. This distinction blocks a convenient explanation that the skin simply tore because decompression was violent. Decompression accelerated the final opening, but the pressure load became catastrophic only after fatigue and disbonding had reduced the joint's capacity. The NTSB placed probable cause on Aloha Airlines maintenance program failing to detect significant disbonding and fatigue damage. That finding concerns a system: inspection design, scheduling, staffing, supervision, execution, documentation, and quality control. Aloha's operation demanded close attention to cycle-driven aging, yet the board found deficiencies in maintenance supervision and inspection quality control. Damage that should have triggered repair or deeper examination remained in service until the joint failed. Maintenance is often shown as one mechanic looking at one panel. Fleet safety depends on a chain of decisions that determines where that person looks, what surface condition is acceptable, what method is used, and what happens when evidence is ambiguous. Visual inspection is powerful when damage produces visible cues and the surface is clean, accessible, and well lit. It is weaker when cracks are short, numerous, hidden by overlap, affected by corrosion, or distributed across a long joint. Multiple site damage challenges a single crack assumption. An inspector may judge each small crack below a critical length while the structure experiences them as one weakened region. Once cracks link, the effective damage is much larger than any individual indication. Non-destructive inspection can add sensitivity, but it also requires the correct method, calibration, coverage, and interpretation. Technology does not rescue an inspection program that asks the wrong location or interval. The NTSB also identified FAA oversight failures. The agency had not properly evaluated Aloha's maintenance program or assessed inspection and quality control deficiencies. Regulatory requirements did not force the complete lap joint coverage proposed by Boeing's Alert Service Bulletin. That difference between recommendation and requirement mattered. An operator can receive broad manufacturer guidance while complying with a narrower mandatory action. If the risk exists outside the mandated area, formal compliance does not equal complete control of the hazard. The board also cited the lack of terminating action after early production problems became known. Repeated inspection manages risk only while it reliably finds damage before failure. A permanent modification or replacement removes the vulnerable condition instead of asking inspection to catch it forever. Aging aircraft rules changed because Flight 243 made cycle history impossible to treat as a secondary detail. Regulators and operators expanded structural inspection programs, records reviews, and attention to high-cycle fleets. The central problem was not that old airplanes are automatically unsafe. Airframes remain safe when their actual loading history, known structural details, repairs, corrosion exposure, and inspection capability are managed together. Calendar age is one input among several. A high-cycle aircraft can demand different inspection timing from a lower-cycle aircraft of the same model and year. Maintenance programs must follow the mechanism that grows damage, not the easiest number to print on a fleet list. Flight 243 is often remembered through one photograph. That image can imply the entire top of the airplane vanished and everything else somehow worked normally. The real structural outcome was more specific and more instructive. The separated upper lobe removed a major section of pressure shell and supporting structure. The floor and lower fuselage remained continuous enough to carry cabin, bending, and landing loads. Frames and skin outside the filled region redistributed forces they had not been intended to carry in that configuration. Fail-safe behavior is not a guarantee that any amount of damage is survivable. It is a design objective. Local failure should leave alternate load paths long enough for detection or safe landing. Flight 243 reached a runway, but its damage exceeded what anyone should accept as a routine demonstration of that principle. The cockpit itself survived because the failure began aft of the forward entrance and the lower structure maintained connection. If the fracture had propagated differently, control cables, wiring, hydraulic lines, or the flight deck attachment could have been compromised more severely. The event therefore contains contingency. Investigators can explain why this joint failed and why the observed airplane remained controllable. They cannot turn the outcome into proof that an upper fuselage separation will usually end the same way. Safety analysis must resist outcome bias. A successful landing makes the surviving barriers visible. It can also hide how close the event came to crossing a boundary where crew skill would no longer matter. Clarabelle Lansing did not return from Flight 243. Her death can be obscured when the aircraft's landing is described as miraculous. The landing saved everyone still aboard, but the accident had already taken one life before the emergency descent began. 7 passengers and 1 flight attendant suffered serious injuries. Dozens more had minor injuries. The open cabin exposed people to forces and debris no normal restraint system is designed to make comfortable. Survival was uneven across seats and positions. The casualty record explains why structural maintenance belongs to passenger safety. A crack hidden under a lap joint is separated from the cabin by no abstract boundary. When that joint opens, the pressure shell and occupied space become the same event. The pilot's emergency descent and landing prevented the structural failure from becoming a total loss. Their task was made harder by deafening noise, damaged communication, uncertainty about the airframe, injured people behind them, and the need to configure for landing. Crew performance belongs inside the causal account but not in place of it. of it. Skill managed the consequences after maintenance and oversight defenses had failed. The safest system is not one that repeatedly demands extraordinary recovery. It is one that detects fatigue before a normal flight produces an open cabin. Flight 243 is therefore both a record of successful control and evidence of unacceptable exposure. The crew saved the airplane that remained. Investigators and regulators had to change the system that allowed it to reach that state. The NTSB issued recommendations to the FAA, Aloha Airlines, and the Air Transport Association. The subjects reached beyond one repair: lap joint inspection, maintenance program supervision, quality control, corrosion, high-cycle aircraft, and structural modification. Later, aging aircraft policy drew on the same principle. Operators must know the service history of each airplane and inspect structural details according to actual risk. Records, physical condition, and inspection results need to agree. A recommendation is effective only when it reaches the work. The final defense is not a report on a shelf. It is a changed task card, a broader inspection zone, a better method, a repair threshold, or a structural modification that removes the vulnerable detail. Modern structural health programs still work against the same physics. Pressure cycles continue. Aluminum still accumulates fatigue. Corrosion still hides at interfaces. What changes is the quality of prediction, inspection, records, access, repair, and fleet-wide learning. Damage tolerance analysis estimates where cracks can begin and how fast they can grow. Inspection intervals are then set so detection should occur before residual strength falls below a safe level. Multiple site damage requires special attention because neighboring cracks can interact sooner than a single crack model suggests. No model eliminates inspection uncertainty. The practical objective is overlapping defense, conservative intervals, suitable methods, trained inspectors, independent quality control, and mandatory action when known construction details show poor durability. The photograph of N73711 at Kahului is an answer image. It shows what happened. It does not by itself explain why. The explanation lives in the joint geometry, the aircraft's cycle history, the durability of the cold bond, corrosion, inspection coverage, maintenance execution, and regulatory scope. That difference matters for every catastrophe with a powerful final image. A dramatic consequence can pull attention toward the last seconds. Prevention usually sits earlier, in quiet technical decisions made when nothing appears urgent. Flight 243 did not need a stronger emergency checklist for an open roof. It needed the roof joint to be identified, inspected, repaired, or modified before takeoff. Aloha Flight 243 reached Maui because enough structure remained and the crew used it. The accident report then traced the missing upper fuselage to damage that had been present before the aircraft left helo. Disbonding changed the lap joint. Corrosion weakened it. Pressure cycles grew cracks at multiple fastener holes. Inspection and oversight failed to remove the airplane from that path. At 24,000 feet, normal cabin pressure completed the sequence. The lesson is direct. Fatigue rarely announces itself with one large visible break. It grows in increments that maintenance is expected to find. When small cracks are allowed to connect, the first unmistakable warning may be the structure leaving the airplane. Explosive decompression is often described as though pressure itself were an explosive chemical. The energy comes from compressed cabin air expanding through a new opening. At cruise altitude, the air outside is thin. Inside, the environmental system maintains a pressure suitable for occupants. The fuselage carries the difference between those two conditions as outward load. When a breach forms, flow accelerates toward it and the pressure difference falls rapidly. A small, stable opening can vent pressure without removing a large structural section. Flight 243 was different because the opening developed along a joint already weakened by distributed fatigue. The escaping air loaded peeled skin and interior panels while the crack path continued through adjacent damaged locations. Decompression and structural fracture reinforced each other during the brief event. Pressure drove separation, and separation created more area for pressure to act through. Once the cabin equalized with the atmosphere, the sustained pressure load diminished, but the aircraft still had to survive aerodynamic forces on torn edges, vibration, maneuvering, and landing. That is why lowering altitude was necessary but not sufficient. The crew could reduce pressure differential and reach breathable air. They could not know whether exposed structure would remain stable during turns, flap extension, or touchdown. Investigators therefore separated the initiating fatigue from the forces that enlarged the damage. The maintenance failure existed before takeoff. The pressure-driven opening occurred in flight. Aerodynamic loads shaped what remained. Landing loads tested the surviving floor and lower fuselage one final time. Treating all of that as one unexplained blast would erase the mechanism's safety programs needed to control. The strongest prevention lesson from Flight 243 is not a demand for perfect prediction. It is a demand that known uncertainty produce wider defenses. The cold bond history was known. Corrosion susceptibility was known. The aircraft's cycle count was measurable. Boeing had proposed broader inspection coverage. Each fact should have pushed the system away from relying on a narrow visual check of selected joints. A robust program begins with configuration and service history for each airframe. It identifies joints built with vulnerable processes, counts the loading events that drive fatigue, and accounts for environmental exposure. It then chooses an inspection method able to find the expected damage at an interval shorter than the predicted growth time. Findings are tracked across the fleet rather than treated as isolated repairs. Quality control verifies that access, preparation, coverage, and interpretation match the engineering requirement. When repeated inspection cannot provide enough confidence, terminating action changes the structure. That may mean replacement, reinforcement, or modification of the vulnerable detail. The expense is visible and immediate. The benefit is an accident sequence that never begins, which makes prevention easy to undervalue until a photograph like N73711 forces the hidden risk into view. Flight 243 gave aviation a severe but incomplete warning. One crew member was lost. Many people were injured. The airplane landed because alternate structure and skilled control remained available. The NTSB's work converted that outcome into requirements and recommendations aimed at high-cycle aircraft far beyond Hawaii. The final measure of those lessons is simple. A lap joint should be repaired because its condition demands it, not because the cabin has already opened around it.